All right, so what we're going to do is we're going to run through your Chapter 9 homework, maybe in a video or two. And so we're just going to dive right in. This first one is really just getting you comfortable with balancing reading about two samples at the same time. We're not really going to do a full test here. And so again, the goal is, hey, can we just get used to understanding that I'm going to need to balance two sets of data at the same time so that I can ultimately later construct the test statistic comparing two proportions. And so here we go. It says, consider the vaccine treatment group to be the first sample. So as I read, well, the vaccine treatment group had that many students, 196, 978. And a success in this case, although it doesn't sound good, is a success, or the thing I'm interested in studying is how many developed the disease after the vaccine. So P1 hat is going to be the 35 who developed the disease out of the total amount that we sampled. And that's an interesting number, but it says round to 8 decimal places. And just remember that that e to the negative 4 means move the decimal left. That's why it's negative 4 places. So that means decimal place 3 leading zeros, then my 1, 7, 7, 6, 8. How many decimal places am I up to? That's 8. And I don't need to round that 8 up because there's a 4 after it. All right. Q1 hat is just the opposite, or in other words, Q is sometimes how they're going to write the 1 minus, where is it? 1 minus P. All right, just to say out loud. So it's the opposite of P, the opposite of my successes. Well, this is a probability. One way we've figured out how to find opposites is do 1 minus what we got before. And you can get your previous answer by pressing the blue second button and then answer right there. So now that's 8 decimal places. 2, 3, 4, 5, 6, 7, 8. For the second sample, grab their n, 132 out of that number. Again, that's a weird one that we have to use our decimal places carefully for. 1, 2, 3, 4, 5, 6, 7, and I'll have to round that up. There's my 8 decimal places. And then that one's complement. So 1 minus, I guess another way you can do it is you can just scroll up. You can't really see it because of the weird coloring on my camera, but it is highlighted on that, and now I can get its complement. So 0.1, 2, 3, 4, 5, 6, 7, 8. Great, that's question 1, just reading through and capturing those data values. Never mind, there's a little bit more. Okay, this is the way that they're going to write P of C. So our P of C formula is, again, just all my successes divided by all of my sample sizes. Well, that's going to be the 35 who got the disease who had the vaccine, the 132 who got the disease who didn't have the vaccine, divided by, well, N1 and N2, so I could write both of those, the 196 and the 195, but I also know how many I totaled in general, so 392, 888 is what I'll get when I add everyone together. Once again, that's a very small number, rounded to 8 decimal places, so 3 leading zeros because of that negative 4, and then 4, 5, 6, 7, 8. And I bet I have to find its complement too. Of course I do. 1 minus that last value to 4 decimal places, or sorry, 8 decimal places. 1, 2, 3, 4, 5, 6, 7, 8. And that doesn't round up. Great, we did it. There's question 1. So just read the problem, identify the values. Up next, now we're going to start to kind of get into our tests. So let's see here. Oh, we also have technology results. So we did not have to do any of this into the calculator. It's right there. Cool. All right, null and alternative hypotheses. Well, right off the bat, I already know it's only going to be A, C, or F because those are the only ones that have equality in their null hypothesis statement. But let's see what we're going to compare. We are going to compare vinyl gloves, latex gloves, and we want to test that vinyl gloves have a greater risk of virus leak, so that the proportion of viruses from vinyl gloves being greater than, and vinyl is the first, the other, and that looks like C. All right, now it says identify the test statistic. Well, it literally has the technology results, and it right there says test statistics, so 10.36 to 2 decimal places. All right, identify the p-value. Again, I've got that right in the table right there. Wow, the p-value is literally 0. And what would I then conclude? So let's just talk about concluding in general. So concluding, no matter what, if the p-value is less than alpha, then here's what we can say. We can say that we're going to reject HO. Can I write that as a subscript? I can't, but we'll just move on for now. We're going to reject HO. That means there is significant evidence that the alternative is true. So that's the way I'm going to say it without context, but we're going to turn this into context. So the thing is, there's 3 simultaneous statements going on. P-value is less than alpha, so we are rejecting HO because there is significant evidence for the alternative hypothesis. Of course, there's the opposite. Whoops, oh my goodness. What have I done? How do I redo? Give me a second here. All right, and we're back. So the other way we conclude is, of course, if the p-value is greater than alpha, then we do not reject HO because there is not significant evidence that the alternative is true. So again, the idea is that we are either rejecting HO or not rejecting HO. We're never saying that the HO is true. We're just saying we either have rejected it or we haven't rejected it. And that's because maybe, well, why would we reject HO? Because there is evidence that the alternative is true. And if we don't reject HO, then we must not have found enough evidence to say the alternative is true. So if the alternative isn't true, we can't get rid of the old assumption yet. All right, so let's see what's going on in our problem. Well, the p-value is ridiculously small. It's essentially 0. So no matter what your alpha is, you're going to be rejecting. So it is less than the significance level alpha. Did they even give me an alpha? It's 0.05. But that's just 0, so it beats pretty much everything. So we reject the null hypothesis, and there is significant or sufficient evidence to support the claim that vinyl gloves have a greater risk of virus leak than latex gloves. And again, there it is with context, but the main thing is that p-value is less than alpha, so we do reject because there is sufficient or significant evidence. So you say those 3 things at the same time, or you logically switch them. The p-value is greater, we do not reject. There's not significant or sufficient evidence that the alternative is true. All right, now this time, this was an easier question because the data was given. This time, we need to get all that data ourselves. So first, let's read the claim. We want to see if men and women have equal success in challenges. So that just pretty much means, is it equal or is it not? So that also looks like C again. What are the odds that the randomization did that? And this time I need to come up with a test statistic myself. So I'm going to go through the long way of actually writing out this test statistic by hand, and we'll see what goes on here. I mean, we're going to use the calculator, but essentially I want to run you through using this formula just once, and then we'll run to the calculator and use it every time for the other examples. So our z-value is going to first be, well, our p1 hat. Let's see here. And we'll do the men first. So men challenged that many referee calls, and the result was overturned 420 times. So p hat of the men is 420 divided by its sample size. So I've got a 0.2952. I'll use 4 decimal places. And the women's is going to be 217. Oops, 217 out of the 767. We get a 0.2829. That ultimately gets compared to 0, or in other words, it doesn't really do anything there. That's just what we have in the numerator. We don't even need to write that minus 0. The hard part is figuring out this P of C and 1 minus P of C. What we at least can do really quick while I'm just writing everything down is I can write down 1 over the sample size from the men, which was 1,423. The sample size of the women was 767. And now it's time to find our combined C. So it's going to be the men's successes plus the women's successes. Make sure you get that total first. We'll wrap this in parentheses. Then divide it by the total sampled. So the men's sample size, the women's sample size, make sure you wrap that in parentheses. So there's my p hat of C. It's 0.2 0.909, and then its complement, 1 minus that number, which is 0.7091. So there's our test statistic, all by hand, and let's figure out what that is. That's going to be, I would type alpha y equals to get a fraction, 0.2952 minus 0.2829 square root of, and let's see here, 0.2909 times its complement, 0.7091, whoops, can't see what I'm typing in the calculator, then parentheses 1 divided by the men's sample plus 1 divided by the women's sample. This is really ugly to plug in. I mean, just remember the fact that we're about to show you how to do this in the graphing calculator and save a lot of time. But some people have to do this on a scientific calculator and do this process every single time. So the 2 decimal places, looks like I'm getting 0.60. I sure hope I'm right. And I am. Now it's the p-value. For the p-value, let me grab a z-table. And let's find the p-value for this. This one's going to be interesting because it's a not equal to test, so the first thing I'm going to do is kind of draw my z-table. There's 0 in the middle, and here's what I got. I got 0.60. And this is a two-tailed test, so I'm going to say, well, what are the odds that I got my result or something more extreme? More extreme is always away from the center. But because this is a two-tailed test, we're also going to say it could have been just as likely that I got this side the same distance away at negative 0.6. So again, I'm going to find the area to the right and then essentially double it, and that will be our total p-value. Well, how do I find the area to the right of the z-value 0.6? Well, I find the z-value 0.60. It's 0.7257. But I don't want the area to the left. I want 1 minus the 0.7257. Again, the z-table can only tell you areas to the left. I wanted, oh, there goes the calculator, the area to the right. So I'm going to do 1 minus that value. So what is that? 1 minus 0.7257. And then I need to, of course, double that because that's the right side, and I want the left side as well, and I get 0.5486. So the total p-value is 0.5486. Uh-oh. Round to 3 decimal places. Whoops, 0.549. There we go. All right, and that p-value is essentially huge compared to the 0.5 or 0.05 or 5% significance level. So the p-value is greater than the significance level, so we are going to fail to reject because there is not sufficient evidence to support the claim. Before we do the rest of the homework, we're almost at the 15-minute timeline here. What we're going to do, oh, never mind, we have to construct a confidence interval also. So this is going to bleed into 2 parts, but here's what we're going to say really quickly. We're going to say that, just remember what the p-value is saying is, the odds that you got this result, if the null hypothesis was true, was 0.549, or in other words, above 50%. And above 50% is pretty likely. So if the null's true and you got this result, that's actually fairly likely, or this would happen the majority of the time. So in other words, what we're saying here is, yeah, we did observe some sort of difference between these two. It's not 0, but it's actually pretty small or pretty insignificant. We got a very small z-value, and it resulted in a p-value, again, that happens almost 50% of the time. So we got a result, or a difference, that's fairly common, or in other words, the difference is probably just from the fact that I sampled a random sample, or didn't take the total population into account. So the difference I observed wasn't significant enough. It's probably just noise. And that's what alpha's there to do. Alpha's there to say, well, we want to make sure we only reject if the noise that I get would only show up 5% of the time or less. Because if the difference I observe only shows up 5% of the time or less, again, the idea is we don't think that we're a lucky person and we found a rare result. We think that our null assumption is false. We think if I found the 5% or less result on my first try, I think the null data must be wrong because that 5% again is relying on the fact that the null was true. If the null was true, your result happens 5% of the time or less. Well, then I must not be a lucky person. I must have not found the rare result. The null must be false, is the idea. So with that being said, we'll then learn what's going on here in this part B and continue through the rest of the homework.